Hello there, students and friends. This video is the second part of my lecture series on alternating current. In the previous upload, we analyzed RLC series circuit without a source. This time, we look at AC circuits which includes a source. In many practical electronic systems, AC circuits involve resistance, inductive reactance, and capacitive reactance. So how do these circuit elements behave in an AC series circuit? Let's find out, watch, and learn. As shown in the figure, a resistor, an inductor, and a capacitor are connected in series to an AC source. We use the symbols small letter VR, small letter VL, and small letter VC for the instantaneous voltages across the resistor, the inductor, and the capacitor. And the symbols capital B sub R, capital B sub L, and capital B sub C for the maximum voltages. And we denote the instantaneous and the maximum source voltage by small letter V and capital letter B respectively. And referring to the circuit diagram, we also denote the following instantaneous voltages. All right, so we have small letter b, meaning the instantaneous voltage across points AD, which actually is across the source. Okay, small letter BR is the voltage across points AB, hence it is the instantaneous voltage across the resistor R. Likewise, we use small letter v sub L, all right, to represent the voltage across points BC or across the inductor. And small letter v sub C, okay, referring to the voltage across points CD or across the capacitor. Analyzing this circuit requires a phasor diagram that includes the voltage and the current phasors for each of the components. All right, so we have here in this figure, letter B, this is the case when the inductive reactance, capital X sub L, is greater than the capacitive reactance, capital X sub C. All right. All right. So we have here the current phasor, the one the represented by the arrow colored black. All right. This current phasor is understood to be rotating in the counterclockwise direction, forming an angle at this instant, forming an angle omega t. Right? So, the voltage across the resistor labeled capital V sub R, which is equal to the product of the current amplitude and the resistance, is also drawn along the same line as the current phasor. Right? In other words, the voltage V sub R is in phase with the current. All right, so phasor V sub R is in phase with the current. That means the angle between them is zero. All right, the angle between the current phasor and the VR, all right, phasor is equal to 0 degrees. Now, The other, what we call voltage phasors, for example, uh, the inductor voltage phasor, represented here by this uh, arrow colored orange in the second quadrant, all right? This inductor voltage phasor leads the current phasor by 90 degrees. So you will notice that the angle between the current phasor and the inductor voltage phasor is 90 degrees. All right. This inductor voltage phasor, of course, is represented by the product of the current amplitude and the inductive reactance, capital X of L. Also, we have the capacity or capacitor voltage phasor in the fourth quadrant, represented here by this shorter arrow colored orange, which is along the same line as the inductor voltage phasor, but they are always in opposite directions. And it will be explained later that the capacitor voltage phasor lags the current phasor by 90 degrees. All right. So if you measure uh, the angle formed by the capacitor voltage phasor relative to the current phasor, all right, that is also equal to 90 degrees, but it is a negative angle, all right, because uh, the phasor current as the reference, we say the angle phi is measured, all right, along the clockwise direction. So from the phasor, from the current phasor, you go clockwise, okay, towards the capacitor voltage. That exactly is equal to negative 90 degrees. All right. So um, as shown also in the phasor diagram, we assume that the source supplies a current I given by the equation small I is equal to capital I cosine omega t, where capital I, of course, is the current amplitude. Omega is the angular frequency, and time or instantaneous time, small t. All right? So since the circuit elements are connected in series, the current at any instant is the same at every point in the circuit. So a single phasor I with length proportional to the current amplitude represents the current in all circuit elements. Again, the potential difference between the terminals of the resistor we are emphasizing is in phase with the current phasor. All right, that means that the phase angle phi is equal to 0, and its projection, okay, the projection of the uh, base of R phasor into the horizontal axis at any given instant, which is labeled here as small letter v sub r, right? So v sub r, small letter v sub r, that's the projection of phasor, capital V sub r, onto the horizontal axis at any given instant. Likewise, for the inductive voltage phasor V sub L, which we know is equal to the product of the current amplitude and the inductive reactance, capital X of L, measures the voltage across the inductor, whose what you call angle, the phase angle relative to the current is positive 90 degrees. So we say that the phasor inductive voltage V sub L leads the current by 90 degrees as shown again in the diagram. All right. If this is the current phasor in the first quadrant, now the angle between the current phasor and the inductive voltage phasor, which is located in the second quadrant, that angle is exactly positive 90 degrees. And the projection of that phasor inductive voltage VL is represented by small letter v sub L. The projection of the phasor capital VL into the horizontal axis at any given instant. The voltage across a capacitor, we say, lags the current by 90 degrees. Its voltage amplitude is labeled as capital B sub C, which is equal to the product of the current amplitude, capital I, and the capacitive reactance, denoted by capital X sub C. Its projection onto the x-axis at any given or at any instant is equal to small letter v sub c. All right? So v sub c is the projection of the phasor capital B sub c onto the horizontal axis at any instant. All right? So again, we also emphasize that the phasor v sub c lags the current by 90 degrees. The phase angle, angle P is equal to negative 90 degrees. All right. Now, the phasor capital B, all right, in the diagram, this is the phasor capital B, which represents the source voltage. Okay, it represents the source voltage, small v, and the instantaneous total voltage, V of AD, across the series of elements. Now, to form this vector sum, okay, what's done actually here in the diagram, we first subtract the phasor BC from the phasor VL. Again, the two phasors, inductor voltage phasor and the conductive or capacitor voltage phasor, are along the same line but opposite in directions. And since x of L is greater than x of C, all right, we get their vector difference and label it as b of L minus b of C. So that vector difference is represented by this dark arrow in the fourth quadrant, all right, along the same line as the inductor voltage. So, the sum of these two, all right, the sum of the two phasors, right, VR, phasor VR, and what we call the VL minus BC phasor, when added vectorially, in other words, when we apply the Pythagorean theorem or formula, all right, the vector sum is represented by this arrow, all right, and that is what we mean or what we call the vector sum. The vector sum labeled simply as capital V, all right. And again, because of application of Pythagorean theorem, we can determine the magnitude of that phasor capital V. So it's just simply equal to the square root of the square of VR, capital VR squared, plus the square of the vector difference, capital BL minus capital BC. So their difference is to be squared. And then added to the square of VR. finally get the square root that will be the magnitude of the phasor B. Alright? When expressed in terms of the product of the amplitude, current amplitude, and the resistance R, so we can also express the phasor V, or the vector sum of the voltage. Likewise, when capital B sub L expressed as product of the current amplitude and the inductive reactance, or capital I, capital X sub L minus, in the case of the capacity voltage expressed as the product of current amplitude and the capacitive reactance, capital XC. Then square it, alright, which, when simplified, can be expressed as the product of the current amplitude and the square root of R squared plus the square of XL minus XC. Okay? So this formula will bring us now to the concept of what we call impedance, capital Z, or impedance. Alright? So impedance is simply equal to the square root of the sum of the squares of capital R and the square of the difference between X of L minus X of C. So impedance is just analogous to what we call resistance in the direct current circuit. Alright? Impedance is the resistance when we are talking about an AC circuit whose definition actually, okay, impedance is just the ratio of the voltage amplitude across the AC circuit to the current amplitude in the circuit. Alright? So, it can also be expressed as capital B equals capital I multiplied by the impedance capital Z. Alright. Now, while the first formula, this one, is valid only for an RLC series circuit, the second formula, this one, B equals product of capital I and capital C, can be used to define the impedance of any network of resistors, inductors, and capacitors as the ratio of the amplitude of the voltage across the network to the current amplitude. Right? The SI unit for impedance is also the unit ohm. Alright, so the impedance of an RLC series circuit also has another formula or version of the formula. This time, it is shown in this equation that the impedance of an RLC series circuit is dependent on the resistance, the inductance, the capacitance, as well as the angular frequency of the oscillation. Alright? So impedance capital C can also be determined using this formula, which is Z equals square root of R squared plus the square of omega times the inductance L minus, right, the reciprocal of the product of omega and the capacitance C. So each of these quantities, right, is defined here. Capital C the impedance of an RLC circuit, series circuit that is, whose SI unit is of course the ohm. Capital R is the resistance, also expressed in ohm. Capital L, the inductance expressed in Henry. Capital C, the capacitance expressed in farad. And the angular frequency, omega, whose unit is of course radian per second. In the figure, the angle phi between the voltage and the current phasors is the phase angle of the source voltage with respect to the current I. That is, it is the angle by which the source voltage leads the current. So figure B here shows the behavior if an RLS series circuit in which the inductive reactance X of L is greater than the capacitive reactance X of C. Right? Now, the other figure, figure C here, shows the behavior when X of L is less than X of C. That is, the voltage phasor V lies on the opposite side of the current phasor I. Right? And the voltage, we say, lags the current. In this case, X of L minus X of C is negative. Alright? So the tangent of the angle phi is also negative. It is the angle between, or an angle that's between 0 and negative 90 degrees. And since the inductive reactance X of L and the capacitive inductance or reactance X of C depend on frequency, the phase angle phi also depends on the frequency, right? And that is shown in this equation for tangent angle phi, all right? Tangent angle phi is just equal to the ratio of omega L minus the reciprocal of omega C divided by the resistance capital R. If the current small I is defined as capital I cosine omega t, then the source voltage small v can be expressed as capital B cosine omega t plus angle phi. All right, so we now have our question number 1. In the series circuit shown, the resistance is 255 ohms. The inductance is 45.0 millihenry. The capacitance is 0.400 microfarad. And the source has voltage amplitude 55.0 volts. The inductive reactance is equal to the resistance. Questions. Find letter A, the frequency of the source. Letter B, the impedance. Letter C, the current amplitude. Letter D, the phase angle. And letter E, whether voltage leads or lags the current. All right, so our solution for question letter A, we're looking for the frequency small letter f. We first determine the inductive reactance capital X of L, which according to the question is just equal to the given resistance big R equal to 255 ohms, right? And then we equate that to the product of the angular frequency omega and the inductance capital L, we will get the value of the angular frequency omega as 255 ohms divided by 45.0 times 10 to the negative 3 Henry. Okay, so simplifying, we get the value for the omega 5.67 times 10 to the third radians per second. And using the relationship between ordinary frequency and angular frequency, small f is just equal to omega divided by 2 pi, right? So that will give us a frequency equal to 902 hertz. For question letter C, we are looking for the impedance capital Z, right? We first determine the value of the capacitive reactance capital X sub C, which is just equal to the reciprocal of omega times capital C. Substituting, we get 1 over the value of the omega, 5.67, times 10 to the third radian per second, multiplied by the capacitance, 4.00 times 10 to the negative 7 farad. So we will get the value for the capacitive reactance equal to 441 ohms. And using the formula for impedance equals square root of r squared plus quantity xl minus xc quantity squared, substituting square root of 255 ohms squared, that's the value of the resistance R, plus the inductive reactance, which is 255 ohms, that's given in the question, minus the computed value for the capacitive reactance, which is 441 ohm. So their difference will be squared, then added to the square of R, and getting the square root, we will get the value for impedance, which is 316 ohms. Next, we determine the current amplitude. Current amplitude capital A is equal to, all right, the voltage amplitude capital B divided by the impedance. So 55.0 volts, this is given in the question, to be divided by the impedance 316 ohms, we will get 174 milliamperes. We will also get the phase angle phi using the formula. Angle phi equals arctan quantity x of L minus x of z divided by big R. Substituting, angle phi is equal to arctan of 255 ohms minus 441 ohms to be divided by 255 ohms. And we will get the value for the phase angle phi, that is equal to negative 36.1 degrees. And answering the question, letter E, whether or not, or whether the voltage leads or lags the current, the answer is the value phi, which is negative 36.1 degrees, okay, means that the voltage lags the current by 36.1 degrees. Moving on to question number 2. For the RLC series circuit given in question number 1, find expressions for the time dependence of the instantaneous current, small letter I, and the instantaneous voltages across the resistor, V sub R. Alright, the instantaneous voltages are denoted as small letter V sub R. This is across the resistor. A small letter V sub L, this is instantaneous voltage across the inductor. And V sub C, small letter V sub C, the instantaneous voltage across the capacitor, as well as small letter V, the instantaneous voltage across the AC source. So for a solution, we first determine the angular frequency omega based on question number 1. Omega is equal to 5.67 times 10 to the third radians per second. And using the formula for instantaneous current small I equal to capital I cosine omega t, all right, we substitute. We are given the current amplitude, all right, taken from question number 1, 174 times 10 to the negative 3 amperes. And the cosine of the angle omega is 5.67, or omega has a value 5.67 times 10 to the third power radian per second. All right. Since we are only asked to find an expression for the instantaneous current, so this will be our answer. All right. At any instant t, the instantaneous current is equal to 174 times 10 to the negative 3 amperes. All right. Multiplied by the cosine of 5.67 times 10 to the third radian per second multiplied by the instant t. And for each of the instantaneous voltages, all right, first we have the instantaneous voltage across the resistor labeled as small letter v sub R. All right, and since this voltage across the resistor, this phasor is in phase with the current phasor. All right, so we just pattern this equation to that of the current I. But the voltage amplitude, which is given as 55.0 volts, to be multiplied to the cosine value of the angular frequency, 5.67 times 10 to the third radian per second, also multiplied by the given time small t. So that's the equation or expression for determining the instantaneous voltage across the resistor. And for the the voltage across the inductor, we first determine the value of the capital V sub L, all right, or the maximum voltage across the inductor, which is the product of the maximum current or current amplitude and the the inductive reactance capital X sub L. Substituting, we have the value of the current amplitude 174 times 10 to the negative 3 ampere and the inductive reactance, all right, taken from question number 1, 255 ohms. Doing our math, we will get the value for the voltage amplitude along the inductor, 44.4 volts. So we can now determine the instantaneous voltage, all right, across the inductor, small letter v sub L. That's equal to big V sub L which is the voltage amplitude across the inductor, to be multiplied by the cosine of Wt or omega t, all right, plus, okay, the phase angle phi, which is positive 90 degrees. When converted to the sine function, this becomes negative b sub L sine omega t, right? And therefore, our expression for the instantaneous voltage across the inductor is just equal to negative 44.4 volts. This is the value of the voltage amplitude along the inductor, all right, taken from question number 1, and multiply that to the sine value of omega, which is 5.67 times 10 to the third power radian per second, to be multiplied, of course, by any value of time t. Right. Next, find the instantaneous voltage across the capacitor. We first determine the voltage across the capacitor amplitude, capital V sub C, which is just equal to the product of the current amplitude, capital I, and the capacitive reactance, capital X sub C. Okay, so substituting the value of the current amplitude, 174 times 10 to the negative 3 amperes, multiplied by the capacitive reactance, 441 ohms. So we get the value of capital B sub C equal to 76.7 volts. So we can now express the instantaneous voltage across the capacitor, small letter b sub c, which is equal to capital B sub c multiplied by the cosine of the angle omega t minus 90 degrees, which when converted to the sine function is just equal to capital B sub c multiplied to sine omega t, or our expression for the instantaneous voltage across the capacitor, small letter b sub c, equals 76.7 volts times the sine of the angle 5.67 times 10 to the third radian per second multiplied by time t. It was noted in question number 1 that the source voltage, capital V, phasor, lags the current phasor by an angle phi equals 36.1 degrees. So, to express the instantaneous voltage across the source, small letter v, is just equal to capital V cosine of the angle omega t minus 36.1 degrees, which when converted to the sine function is equal to capital B sine omega t. So, for a final answer, we may express the instantaneous voltage across the AC source in terms of the cosine function, which is 55.0 volts multiplied by the cosine of the angle 5.67 times 10 to the third power radian per second multiplied by t minus 630 radians. This is the radian equivalent of 36.1 degrees. Or you may also use the sine function v multiplied by sine omega t. That is, small v can also be expressed as 55.0 volts multiplied by the sine of the angle 5.67 times 10 to the third radian per second times t. Down to our last question, number 3. The current in an RLC series circuit has amplitude 0.120 amperes and angular frequency 8.00 times 10 to the 3 radian per second, and it has its maximum positive value at t equals 0. The resistance is 95.0 ohms, the inductance is 6.50 millihenry, and the capacitance is 0.440 microfarad. For the resistor, inductor, and capacitor, find letter A, the voltage amplitudes. Letter B, the instantaneous voltages at time equals 0.305 milliseconds. So our solution, for letter A, we first find the voltage amplitude across the resistor, labeled as capital B sub R, which is simply equal to the product of the current amplitude and the given resistance, big R. That is 0.120 amperes times 95.0 ohms. So we get that value for capital B sub R equal to 11.4 volts. Next, for the voltage amplitudes across the inductor, capital B sub L, which is equal to the product of the current amplitude, capital I, and the inductive reactance, capital X sub L. All right? So multiplying the current, which is 0.120 amperes, and inductive reactance, capital X sub L, is just equal to the product of omega and the given inductance, that is 8.00 times 10 to the third power rad or radian per second times 6.50 times 10 to the negative 3 Henry. Simplifying, we get this value for the voltage amplitude across the inductor, which is 6.24 volts. And for the voltage across the capacitor, capital B sub C, also known as the voltage amplitude across the capacitor, also equal to the product of the current amplitude, capital I, and the capacitive reactance, capital X sub C. Substituting, the given current amplitude, 0.120 amperes, and the capacitive reactance is simply equal to the reciprocal, the product of omega and the given capacitance. So that means 1 over 8.00 times 10 to the third power radian per second multiplied by 4.40 times 10 to the negative 7 farad. Alright? 0.440 microfarad converted to farad, that's 4.40 times 10 to the negative 7 farad. And doing our math, once again, we will get the value for the voltage amplitude across the capacitor equal to 34.1 volts. For question letter B, you are asked to find the instantaneous voltage across the resistor, labeled here as small letter V sub R. That's simply equal to big letter V sub R. This is the voltage amplitude across the resistor to be multiplied by the cosine omega t. Substituting, we have 11.4 volts multiplied by the cosine of the angle 8.00 times 10 to the third power radian per second multiplied by the given time, which is 3.05 times 10 to the negative 4 seconds. Simplifying, we get 11.4 volts times the cosine of the angle 2.44 radian, which is actually, when simplified further, is equal to negative 8.71 volts. Now, for the instantaneous voltage across the inductor, labeled small letter v sub L, alright, it's just equal to the negative of the voltage amplitude across the inductor multiplied by sine of the angle omega t. Substituting negative 6.24 volts times sine of the angle 8.00 times 10 to the third radian per second to be multiplied by the given instant or time 3.05 times 10 to the negative 4 seconds. Simplifying, we get negative 6.24 volts multiplied with the sine of the angle 2.44 radian, which is impact equal to negative 4.03 volts. Now, for the instantaneous voltage across the capacitor labeled as small letter v sub c, which is equal to the voltage amplitude across the capacitor, capital V sub c, multiplied by sine omega t, which means 34.1 volts, multiplied by the sine of the angle, 8.00 times 10 to the third power radian per second, times the given time 3.05 times 10 to the negative 4 seconds. Simplifying, we get 34.1 volts multiplied by the sine of the angle 2.44 radian, or small letter v sub c is equal to positive 22.0 volts. So that's it. We are done with our video tutorial. As usual, thank you very much for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.